Welcome back, focused learners, to another explainer. I am absolutely thrilled to have you here today because we're going to demystify the abstract, often completely invisible digital infrastructure that runs our modern world. I mean, think about it. It's the invisible scaffolding behind literally every purchase you make, every map you use, and every single organization that functions around you.
Okay, let's dive into this. Have you ever actually stopped to wonder what exactly happens when you slide your debit card into an ATM? You press a few buttons and magically, cash just appears. We interact with these intensely complex systems every single day without even realizing the sheer scale of the engineering that's happening right behind the screen.
To truly grasp these complex technologies, we first need to build a really solid foundation. So, what exactly is a system anyway? Well, at its core, a system is simply a group of interrelated components working together to achieve a common objective. Whether it's the smartphone in your pocket, a massive company's payroll software, or that ATM machine on the corner, they all share this exact same fundamental DNA. And because they share that DNA, every system has the exact same core anatomy, which breaks down into three really simple steps. Let's use our ATM example again. It always starts with an input. That's you entering your card, your PIN, and the amount of money you want. Next up is the process, where the machine encrypts and processes that transaction with your bank. And finally, the output. You get your cash and a receipt showing your updated bank balance. Every single system you will ever encounter operates on this exact basic logical flow. Input, process, output. So here is our roadmap for today. We're going to cover 1. What is a system? 2. The rise of automation. 3. The information system ecosystem. 4. Building systems using the SDLC. And 5. Choosing the right model. Section 1. What is a system? Let's categorize the digital and physical. Now, systems can be broadly categorized by their behavior, and a great place to start is the contrast between open and closed systems. Open systems, they constantly interact with their environment. They take inputs from the outside world and release outputs right back into it. Think of a bustling hospital receiving new patients, or even something as simple as your refrigerator at home, taking in electricity and warm air to output cold storage. On the flip side of that, we have closed systems. A closed system exists entirely alone with absolutely zero external connections. A really great natural example of this is the human blood circulation system, which operates entirely within its own closed boundaries. Section 2. The rise of automation, the shift in speed and cost.
Before computers, organizations relied completely on manual systems. These were driven heavily by human labor, massive, towering stacks of paper, and endless rows of file cabinets. And as you can imagine, they were notoriously slow, highly prone to human error, and incredibly costly in terms of salaries and wasted time. Contrast that with automated systems, which are this brilliant combination of hardware and software. Automated systems allow for real-time monitoring, lightning-fast calculation speeds, and incredibly efficient digital storage. When you put them side by side, it becomes instantly clear why businesses absolutely desperately needed to evolve. They simply couldn't survive the modern pace using paper and pencils. Section 3. The information system ecosystem, the digital brain of an organization. Now, I know this might feel a little bit like an alphabet soup of acronyms at first, but don't let it overwhelm you. Let's just pace ourselves and group these acronyms by their corporate function. Right at the operational base, the foundation, we have TPS for handling day-to-day transactions. Moving up a level, we have MIS, which takes that raw data and summarizes it for managerial operations. Higher up still is DSS, providing deep data analysis for decision support. And finally, at the very top of the pyramid, we have ESS, delivering critical strategic data to executive leadership. It's actually a perfectly structured hierarchy. And this brilliantly illustrates that foundational layer we just mentioned, the Transaction Processing System, or TPS. Whenever you book an airline ticket or buy a pair of shoes online, you are interacting directly with a TPS. It operates entirely in real time, instantly gathering your credit card data, processing the payment, updating the seller's inventory, and securely logging the record. It really is the absolute lifeblood of modern digital commerce. Another incredibly visual and honestly really cool system in this ecosystem is the GIS, or Geographical Information System. Instead of just staring at spreadsheets full of numbers, a GIS captures and displays data related to physical positions on the Earth's surface. By overlaying data points like streets, buildings, and vegetation all onto a single digital map, it helps users instantly analyze spatial patterns and relationships. It's exactly how city planners design traffic routes or how massive logistics companies track their entire delivery fleets. Section 4, Building Systems, the SDLC, moving from theory to actual construction. Whenever you need to build something really complex, you need an instruction manual. And that is exactly what the SDLC, or System Development Lifecycle, is. It is a set of process models that provides vital, step-by-step guidance to developers. It essentially exists to answer one constant, absolutely critical question. What should be done by the development team right now, and what do we do next? It's the ultimate blueprint for creating those automated solutions we just finished talking about. Section 5, Choosing the right model, exploring different philosophies of software construction. Let's start by examining the most traditional philosophy of them all, the waterfall model. Just like water, it flows in a strict, linear, sequential direction, starting from a feasibility study, cascading down to design, coding, testing, and finally landing on maintenance. The absolute, unbreakable rule of waterfall is that phases do not ever overlap. A new phase only begins when the previous one is entirely, 100% complete. The output of one single step becomes the direct input of the next. So the crucial point here is understanding the real-world trade-offs of this strict approach. The pros of waterfall are fantastic if you love organization. Progress is highly visible, the documentation is crystal clear, and because it's so step-by-step, correcting errors in those early stages is a breeze. However, the cons are pretty significant. It takes a much longer time to develop a system, and because you literally have to wait for every single step to finish linearly, the client sees a working version of the software very, very late in the process. It's great if your requirements are perfectly stable, but it's pretty terrible if things suddenly need to change. Now, what's really interesting about this slide is how it contrasts with Barry Boehm's 1986 spiral model. Notice how instead of dropping straight down like a waterfall, it loops iteratively through 4 specific quadrants, determining objectives, identifying risks, developing and testing, and then planning the next iteration. It literally looks like a coiled spring, expanding outward with every single round of development. The absolute defining focus of the spiral model is risk analysis. And in software, risk simply means something could go wrong. Because the spiral model constantly reevaluates risks with every single loop, it's perfect for medium to high-risk projects where the initial functional requirements might be, well, a little unclear. It effortlessly accommodates changing requirements. But there's always a catch, right? The trade-off is that management is highly complex, and it can be incredibly expensive to run these constant iterative loops, which makes it totally overkill for small, simple projects. Finally, we have the prototyping model. I like to think of this as the ultimate trial and error cycle. Rather than planning everything perfectly upfront, developers gather requirements, make a very quick design, and immediately build a limited functionality prototype. Then, they hand this directly to the user for an initial evaluation. The user gets to say, hey, I like this, but I absolutely hate that. And the developers refine the prototype based on that quick feedback before moving to final implementation. It heavily prioritizes early customer satisfaction and rapid communication. Conclusion: the future of systems. I want to leave you with a really provocative thought based on everything we've uncovered today. We are currently witnessing the absolute explosion of AI-powered expert systems. These are programs loaded with the entirety of human knowledge in specific fields, capable of thinking and advising almost exactly like real humans. If the foundational rules of input, process, and output are now being handled by artificial intelligence that can actually rewrite its own code, how on earth will the SDLC adapt? What will the interconnected systems of tomorrow even look like when the systems themselves start doing the building? It's a thrilling, maybe slightly terrifying frontier, and I hope this explainer has given you the solid blueprint you need to understand whatever comes next. Thank you so much for learning with me today.